Hi everyone. So today we're going to try to finish up 4.4. So the last thing I want to talk to you about is the following. As you probably expect, after we talk about kind of derivative, we kind of have to talk about this tangent plane of a parameterized surface. So we call from the following. So in here, when I say tangent plane, I do want to kind of specify that we actually refer to, we talk about a two plane, a tangent two plane. Okay. So we call the parametric representation of a plane, based on what we learned in chapter 1, parametric representation of a plane will require the following. Require two direction vectors and one position vectors. Okay, so we have both of those, then we'll be able to write a plane. And if you think about it, given, let's say given a function f that met from R2 to Rm, assuming that m is greater than or equal to 3, so there won't be just from R2 to R2, but let's say R2 to at least R3 or higher. And let's say this function is f of uv. F of uv will have two vector partial derivatives. And what are these vector partial derivatives? Remember, they are basically standard tangent vectors. For the coordinate curve. And since we have two standard tangent vectors, they're both direction vector, we would satisfy the two direction vector that we need to form a plane. And obviously, wherever we form these two standard tangent vector will have to be a specific position on the surface, therefore would satisfy the position vector also. And therefore allow us to actually use these to form a tangent plane. So here become the tangent plane formula. The tangent plane so the tangent plane for a function f that met from R2 to Rm, and remember m have to be greater than 3 or greater, at a specific value, let's say u sub 0, v sub 0, is given by this formula. Notice that this tangent plane formula is specific to this type of function. You probably already noticed that because we have a lot of tangent formula, and they could be very similar, but they all slightly different because of the function that we use it on. So this one will look something like this. Will be vector x equal to, yes, notice is vector x equal to, therefore indicate that we have a parametric representation. T sub 1 multiplied by df over du evaluated at u sub 0, v sub 0, plus T2 times df over dv evaluated at u sub 0, v sub 0, plus f of u sub 0, v sub 0. So in this expression right here, obviously this vector x is our position vector in Rm, because our function map into Rm. Our T1 and T2 are going to be our parameters. df over dv and df over du are our vector partial derivative. Okay, they are our direction vector in Rm. And what is f of uv? That would be our position vector, which is in Rm also. So therefore, we know that this tangent plane formula is for Rm because of all the vectors involved, and there should be three. The two direction vectors and a position vector, and of course, then we have our variable vector, which is on this side. Okay, or maybe I should actually write that instead of position vector. I'm going to write variable vector. There you go, much better. Okay? And important to identify that these two direction of vector partial derivative have to be evaluated at the point where you form the tangent plane. Otherwise, it would not be a two fixed direction vector and therefore would not be able to form a plane. Now, maybe I'll show you a very simple example just to kind of illustrate. Okay. So here's maybe a first example. Let's use the function that we have been working with. U cosine v, u sine v, v. And let's say the question will probably ask you for something like this. Find the tangent plane at, and then I give you a point to do it. So let's say 1 pi over 6. Okay. So therefore, in this case, that would imply that u sub 0, v sub 0 will be 1 pi over 6. So now it's just a matter of using the formula. So to use the formula correctly, I do need three different vectors. One position vector and two direction vectors. So let's start with our position vector. Our position vector will be f of 1 pi over 6. So that just becomes 1 times cosine of pi over 6, which you should know what cosine of pi over 6 is because you came from BC Calculus. That's what expected of you from BC Calculus. Cosine of pi over 6 is root 3 over 2. And then 1 sine of pi over 6, which is 1/2, and then pi over 6. So that would be my position vector. So the next thing I need would be my derivative. So I'm going to do df over du, which we actually did that before. That is cosine v sine v 0. So therefore, df over du evaluated at 1 pi over 6 would equal to cosine of pi over 6, which we already established is root 3 over 2. Sine of pi over 6 is 1/2, 0. Then the next thing I need would be df over du. So I'm going to do it right here, df over dv. So we also did that before, which would be negative u sine v, u cosine v1. So therefore df over dv evaluate at 1 pi over 6 would equal to negative 1/2 root 3 over 2, 1. So now I'm ready to put these three things together. So I have the position vector after my two direction vector. Notice that the two direction vectors are numbers, not variable. Important to remember not to do that. So my tangent plane would be vector x equal to t1 multiplied by radical 3 over 2, 1 over 2, 0, plus t2 multiplied by negative 1/2, radical 3 over 2, 1, plus root 3 over 2, 1/2, pi over 6. Now let's try another example. Let's see. Okay. Let's try this one. Let's say we have f of uv equal to u square v, uv square, u square plus v square. Okay, so once again, this form a surface. This function mapped from R2 to R3. So therefore, it's a surface, two-dimensional surface in R3, and we're going to try to form the tangent plane of it. So let's say the question asks you to find the tangent plane at, let's say 2, 1. So same exact concept. So in this case, 2, 1 is our u sub 0, v sub 0. So therefore, the three vectors that we want would be f of 2, 1. So that would be 4, 2, 2 squared plus 1 squared is 5. df over du is equal to, so you probably remember we did the top two coordinate already. So that would be 2uv, v squared, 2u. So df over du at 2, 1 would equal to 4, 1 squared is 1, 2 times 2 is 4. And df over dv would be equal to u squared 2uv 2v. So df over dv, the value of 2, 1 would equal to 4, 2 times 2 is 4, and then 2. So therefore, in this case, our tangent plane will be T1, 4, 1, 4, plus T2, 4, 4, 2, plus 4, 2, 5. So pretty straightforward for this one. Good. Now, important to understand is that now we have two different tangent plane formula. They're both for tangent plane in R3. So therefore, it's very important that you kind of sort them out. So right now, what we have are two different tangent planes formulas. So important to understand the similarity and the differences between them, so that way you don't get confused. So just a quick summary of these two different tangent plane formula. So in 4.2, we have this formula. We have function f that maps from R2 to R. In this case, f is an explicit function. And f represent a surface. If you want to say two-dimensional surface, you can. A surface in R3. And we have this function look something like this, f of xy equal to z. That's how the function f will look like. And the tangent plane, the tangent plane for f of xy at, let's say, a specific point AB is given by this formula. Z equal to f of AB plus df over dx, the value at AB, multiplied by x minus a, plus df over dy, evaluate at AB, multiplied by y minus b. And that formed the tangent plane at AB. Important to notice is that this is a tangent plane in rather an explicit form also. Because z is technically the dependent variable and is by itself with the rest of the equation on the other side. And this can be rewritten into a standard form. Now, how does that compare to the formula that we just learned in 4.3? In 4.3, we're dealing with a function that map from R2 to Rm. And in this case, f is a parametric representation. And f represent a surface. Once again, if you want to say two-dimensional surface, you can, in Rm. Notice that in 4.2, we are defining a specific surface in a specific dimension, R3 only. While in 4.3, when we use a parametric representation, we can define this two-dimensional surface in any dimension that we want. In Rm, where m could be anything from 3 to 4 to 5 to 6. So therefore, in 4.2, the function f that map from R2 to R only define a two-dimensional surface in R3, while in 4.4 is what I meant to say. In 4.4, the parametric representation of a surface, f map from R2 to Rm, can form a surface in R2, R3, R4, R5, R6, R7, and so on and so forth. So therefore, in 4.4, the parameterized surface definitely is more flexible because it allows us to form surface in higher dimension. Okay? In this case, the function would be f of uv equal to some position vector, vector x, which could be xyz or xyzw or x1, x2, x3, x4, x5, and so on and so forth. And in this case, the tangent plane for f of uv at the point u sub 0, v sub 0 is given by this formula. Vector x is equal to df over du, evaluate of u sub 0, v sub 0, multiply that by t sub 1, plus t sub 2, multiply df over dv, evaluate of u sub 0, v sub 0, plus f of u sub 0, v sub 0. And notice that this is also a parametric representation of the tangent plane. And is that a surprise? Shouldn't be, because the function is explicit and our tangent is also explicit. If our function is parametric, then our tangent is also parametric. Okay? Alright, I think that's the last thing that I want to show you in 4.4 is tangent plane. So make sure that you remember the formula right here. Okay, and also make sure you understand the differences between this formula versus the one that you have learned in 4.2 or 4.3 actually. Okay, yeah, actually it's 4.3. Let me fix that right here. Yep, you learn partial derivative in 4.3 and then 4.4. All right. So that's it for chapter. That's it for the entire chapter 4. So next we'll go on to chapter 5, which we'll go talk more about derivatives. And before we get to chapter 6, where we're going to try to find application for it. All right, I'll talk to you guys soon. Okay, bye bye.